Thank you everyone for joining us on today's webinar. We're going to be talking today about metal leaching and acid rock drainage, which is always a very exciting topic, I think. Um, just to let you know what to expect, we're going to be recording this webinar for future use. Be posted on our website. We'll go through this bit of an introduction. The webinar itself will last about 40 minutes, and then we'll have a Q&A session afterwards. So feel free to use the chat or the Q&A feature in the webinar platform to submit your questions, and I'll pose them to Pete. Who's VEI? If you're not aware of us, we've been around for 20 plus years. We were formerly called Vertex Environmental. Now we're VEI Contracting, specialized environmental remediation contracting firm. Also do construction dewatering and general contracting. My name is Kevin French. I'm the Vice President, Environmental Engineer. And VEI said we work across Canada, which is in fact true. We've worked from coast to coast to coast, as you can see here, as also are doing more work internationally now as well. So wherever the jobs go, we can follow. In terms of our services, here's a list of the different services we provide. Today, we're doing this one here down in the lower right corner, Outreach, which is our educational platform, trying to disseminate some information to the environmental community on capabilities of new technologies and things like that. But everything we do, as it says at the top here, really relates to taking complex environmental data and converting it into some form of a delivered solution to solve your problem or deal with your pain point. There's been a few past webinars. These are going to be posted shortly on our website. Everything from dewatering and high resolution site characterization to dealing with LNAPL on risk assessment sites to PFAS treatment. But as I said, today we're talking about metal leachate and acid rock drainage. There's some other upcoming talks happening tomorrow. There's Bruce Tunnicliffe is presenting at the ESA PFAS Symposium in Calgary. There's another webinar on December 10th on data-driven design. And then we will be doing a short course on conceptual site modeling at next year's REMTech East in Ottawa. So stay tuned for details on those. And more importantly, maybe not more importantly, but interestingly, there's a series of conferences coming up that we help to organize called Smart Remediation. We've always done them in different cities across Canada. This year, we're returning back to Western Canada. So we have an event in Vancouver, one in Calgary, and then Toronto and Ottawa. So if you go to the smartremediation.com website, you can see all the details for those and sign up. Um, and now I will turn it over to Pete, who will take over in terms of the main show.
All right, thanks, Kevin. Future presentation, we are going to get into the advancing the design and performance of long-lived passive treatment barriers for metal leaching or acid rock drainage. Quick overview of what we'll go through today. I want to do kind of a general introduction of metal leaching acid rock drainage. I want to also talk about permeable reactive barriers, very mature technology we use in many sites, including some mining sites. But then we're going to talk about big improvements in the design and implementation of PRBs in the last 25 years that would then, if you're looking at implementing for dissolved metals, this is material. You can get a better result out of your projects. I've been doing contracting for over a decade, 25 years in the industry. My background, master's in environmental engineering from Stanford. Basically, this is all I've ever done in my professional life. And I'm so old that I'm going to tell you stories about the very origins of permeable reactive barriers and what we used to do to contrast it with how much better performance is now. On mine sites, that can be put in essentially permanently, which if you're in the contaminated sites industry, that makes you kind of think about permeable reactive barriers. They are permeable barriers. They act passively, but we tend to call them permeable barriers because what we're doing is we're burying permeable materials. We're placing permeable reactive materials along the groundwater flow path. So as water flows through the permeable barrier, it interacts with the material in the barrier, and you have the destruction or the immobilization of the contaminants. And this is fairly mature technology. It's been in the field since the early 1990s. We'll talk about that in a bit. And so we can predict performance. We use this. We built dozens. VEI has built dozens in more urban areas for a whole contaminant mix, including in some cases dissolved metals. You are able to passively treat the groundwater plume, and it is extremely long lasting. These things are designed to last several decades. There are many examples of walls that are continue to perform 30 years after installation. The fit, obviously, with mine sites is clear, and you see that also in remedy selection guidance. Do you have a long-term mining influenced water problem? Oh, okay, I do. Can you get rid of the source? Oh, no, I really can't. So now your question is, do you want to spend potentially forever actively pumping and managing that water? And if the answer is no, one of your key alternatives is a permeable reactive barrier. And in fact, actually, some of the very first PRB designs were actually on mine sites. So a lot of us in traditional contaminated sites think about the first PRB being like first full scale being Sunnyvale, California, chlorinated solvents, roughly 1995. Same group of geniuses out of University of Waterloo, where so much of this technology came from. 1995, we're up the Nickel Rim mine site, the Falconbridge site, building a sulfate reducing biobarrier. So the acidity wasn't too bad here, but what you had was tailings, old tailings, oxidized tailings, leaching into the groundwater, and it was possible to intercept it. Those first generation barriers that we built, some of them were over-designed, but then when it meant mainstream, and I recall this personally, across the industry, we had a lot of rule of thumb approaches for building them. You would, late 1990s, early 2000s, you dig in a trench, you're trying to intercept the groundwater plume, you mix up zero valent iron. I can remember sourcing iron filings from as basically industrial byproducts, right? Just mixing it up. Maybe you're trying to use a magnet to then back check how much iron is in each piece of backfill. You dump it all in the trench and you just basically hope for the best, right? And so if you haven't really understood the groundwater flux, the residence time of the barrier, if you haven't gotten the barrier materials right, you fail. And all of that effort, that huge capital expense, because we have no operating expense, but that huge capital expense is potentially wasted, right? And if you over design, well, you've wasted a tremendous amount of money. And then none of this, of course, deals with complex sites, complex flow paths, or complex geochemistry, like in the mining world. So is there a better way to do PRBs? And the answer is yes. In the last 20 years of installing these for many different contaminant types, there's a number of very significant improvements that we should all be looking at in putting permeable reactive barriers in the ground. The first is I think we have a industry-wide a better understanding of site characterization. You know, back in the day, it was clear you needed to have boreholes along the groundwater flow path and then, you know, across it. You were looking at the geology, you made some estimates of conductivity. Absolutely. Necessary, but not sufficient. What we found, what meta studies have found, when researchers have gone back and pulled as many case studies as they can, the vast majority of permeable reactive barriers work very, very well. About 10% in some studies did not work well, but when they look at why, it was not the reaction chemistry. It was a failure in the conceptual site model. It was stuff like not understanding seasonal variation in groundwater flow, not understanding mounding, not understanding bypassing relationships. And it was a conceptual site model, not the reactor design. And this is fascinating, and we can act on it. We can solve this problem. I will make a side note that also, I'll talk about installation methods later. You can build out a barrier, especially if we're injecting it. We can add material, so it's not a complete disaster, but certainly if you're going to do it, it's better to do it right the first time than try to go back and fix it. And so doing it right the first time means using the right design software and building a three-dimensional conceptual site model that accounts for spatial heterogeneity and it accounts for seasonal variation. And then not even to touch fracture systems, which are their own kind of set of complications. So how would you build a 3D network? a 3D conceptual design basis. Well, that brings us to improvement number two is tremendous improvements in doing alignment profiling. So you have the data set and you can even assess the variability of key parameters plus the estimated maximum and minimum values for the areas of interest. And one way you get that data density is with just pushing sensors. That's a totally this is a high resolution site characterization direct push probes available in Canada since at least 2011. Just like thousands and thousands of meters of pushed probes. One of the probes we can push nowadays actually is a hydraulic profiling tool. So you're injecting fluid into the subsurface, you're looking at the uptake rate and the pressure dissipation. And what that's going to let you do is it's going to let you look at very fine scale changes in hydraulic conductivity. So here you have a traditional borehole, you're always doing those. You need to physically inspect the material, you need the grain size analysis and so on. But then around it, we can do rapid pushes with no spoils and then look at the pressure dissipation and back calculate K. And so, for example, just in this random example, you can see that there actually is a high K band right on top of that sand underneath the clay that could be important for hydraulically controlling that site. And here, in fact, actually is a complete data visualization on a site that VEI did recently in Southern Ontario. And what you'll see is the variation of K. Sometimes orders of magnitude changes, within a 6 centimeter to a meter and a half scale. Incredibly important in making sure that the barrier is designed properly and you have the residence time in the barrier and you're accommodating for the plausible range of flux scenarios. And that would, knowing the flux and understanding this full conceptual site model brings us to improvement number three, which is the past 20 years has really led to a deep understanding of a wide range of permeable reactive barrier chemistries. And I'm not going to go into this chart here. I'm just going to illustrate that we actually at this point have full-scale applications that you can look at as reference cases for so many things. Radionuclides, obviously dissolved metals, PFAS even, right? There are different barrier designs which we could spend hours on. I want to come back and just talk about ZVI as probably one of the most well-known materials. I think it's applicable to mine sites, and it's a great example of some of the other improvements that we've made to PRBs. Zero valent iron, essentially just elemental iron. Lots of different surface reactions. It's an interesting reductive chemistry. It plays well with even with biological treatment pathways. And I guess the key point here on ZVI is having built hundreds of these within the industry, that we have multiple sources of this material. It's reliable quality. We know its performance. And we can go back and we can look at some of these suppliers and we can look at their walls successfully performing. In some cases, it says 20 years. I'm aware of at least one case where now 30 years after installation, she's doing fine. What could you do with ZVI in a dissolved metals context? Well, directly just through abiotic processes because of the reduction in the vicinity of the iron, because of coprecipitation, because of absorption onto iron products, you can drop most of these multivalent cations over here on the side to the left. Basically anything in pink here, you see the kind of pink fleshy tone? You can get significant contaminant reductions simply through abiotic processes on a reactive iron mixture. But you say, well, what about the biobarrier? Iron plays very well with biological systems as well. There is a whole bunch of interesting sulfate reduction chemistry purely on iron, but it also creates a good environment for biological sulfate reduction. And then you're getting like metal sulfides coming out. You're getting the processes that you saw with even that old 1995 Falcon Bridge one. Now, with both the abiotic processes and the biotic processes, well, you're probably saying to yourself, well, wait a second, how do you do anything at pH 2? Well, we can build that into. We have reactor recipes to buffer different types of solutions coming into the barrier. And often it is as simple as adding limestone or a dolostone, provided that you have a nearby source of relatively high quality. I'll caution you that there have been a couple of cases where they didn't adequately characterize the buffering rock and it was introducing other things into the barrier system. But in general, crushed limestone actually has plenty of case studies, plenty of references. We've used the material ourselves, and it resolves some of the chemical concerns. But if you still have chemical concerns, actually you should have chemical concerns. Big improvement, the next improvement is, right, we have a great conceptual site model. We have 2 or 3 obvious reaction chemistry candidates. big improvement is to do bench scale testing. If you are from the mining space, you're like, oh, shake flasks. This is the other type of the shake flask that you do is to see whether you have an acid generation problem. This is a shake flask to solve the problem, right? We mix it up. We can rapidly screen a couple of interesting or obvious solutions with site water and get a great feeling for what is feasible, and then go to this, which are flow through studies. And I'm going to highly recommend this. This is a huge improvement in professional practice, especially in complex chemical situations. Because although you can model this, freak and everything else, you can do very complicated models. At the end of the day, it is extremely, extremely useful to run real site fluids, real site water through what you intend to use from the actual vendor. We've seen differences in the performance of iron between different vendors. Run it through a column. It's not that huge an expense on an installation that may last 20 or 30 years, and you will see whether you're going to have a problem with passivation, with carbonate fouling, with any of these problems. And you can even solve it in the column stage. So, what do we see with the use of iron? Just continuing with that example. Our lab does dozens and dozens of tests over the years. And so we compiled some of the metal-specific data for this presentation. And what you're seeing is across a couple dozen different studies that generally we're seeing a 2 to 3 order of magnitude reduction in of these types of dissolved metals. So you got your arsenic, you got your cadmium, your copper, your chrome's over there, you got nickel over here. Not surprising, because if you go to the literature, that's what other people see as well. In general, it is well established that these iron-based systems can typically clear 99% or better of many of your typical metals of concern. Hugely useful, although again, you want to look at your site-specific chemistry. Which brings us to improvement number 5 in the implementation of PRBs, which is that old school, you had some basic numbers, you figured your flux, your loading, you would contact time, sometimes off a benchtop, sometimes not always, depending on literature value, but then huge safety factors. And it was a very simplistic design. Well, we still start there, of course. But now remember, we have a sensitivity analysis and we have a comprehensive site model, and we've done column testing. So we understand what parameters are likely to affect the performance of the barrier. And we also understand the likely range in those parameters in the field implementation. So what we can do is we can make sure that our barrier is designed with sufficient but not excessive safety factors. We're going to look at what's driving potential barrier failure, and we're going to make sure that that's covered, but we haven't necessarily gone above and beyond that. And I'll cutting to the chase, actually, in our internal analysis, and I think this is reflected in industry, the biggest sources of variation in the design are the contaminant concentrations and the hydraulic conductivity. So now you have a really comprehensive picture. You have a conceptual site model. You have a design that's robust, but not overly robust, because you did a sensitivity analysis and you knew where you were vulnerable, and that's what you addressed. You didn't just pile tons of material into the ground for the heck of it. So now let's put the material on the ground. Huge, huge, huge improvements in recent years. Old school, dig a trench, still works, love it. You got a couple of problems here. One is it works best if you have stable ground conditions and it's very, very shallow. We could keep that trench open with a guar slurry. Absolutely, no problems. I've got a marsh funnel up there. We can hold it open with a slurry. Some formations still are going to have trouble. You're still going to have trouble with grade. You're going to have trouble with difficult access. It's depending on where you are and what equipment you have access to, could be problematic. Not that huge an issue. If you are from a mining background, you know how we use grouting to do seepage cutoffs, right? You do a row of primaries, you do a secondaries, tertiaries, and you overlap the injection of low permeability materials to have a comprehensive flow barrier. We do it the other way. You can do overburden injection where you're putting in permeable materials and you're overlapping those shots so that when the particle flows through that reactive zone, it will contact the reactant for a sufficient amount of time. Do a lot of these. We say, well, I can't direct push into rock. If we have reasonable characterization of the rock and we can actually identify discrete fracture sets in the rock that are carrying the contaminants, we know where the flow zones are, you build straddle packer systems. That's, I think, the go-to. There are a couple of other ways of approaching this, but right now we are building these straddle packer systems. We've actually even sent a few down to the States for one of our friends down there. And the idea is that if we know where the water-bearing fractures are, we can drop the string, inflate packers on both sides of the injection zone, and then pressure inject into specifically that fracture set. And if we repeat this, we can load enough reactive material into the fractures that you've effectively, the water will still flow, but the contaminants are stuck. It's not bedrock, but it's still difficult ground condition, I can't direct push, that's okay. We can pre-drill. We could ODEX this. We could sonic it. And we've used this method in a couple of places. Lower mainland, Vancouver, really tough tills. Works fine. Sonic down, bentonite backfill, and then you reinsert the injection line, which is this type of high pressure jet. It cuts through the bentonite, so just a thin bentonite sheath there that's keeping the hole open. Cuts through, and you build then those overlapping regimes of reactant. So we can get it all into the ground. A final big piece of improvement in professional practice that would make these far more reliable if you're going to try to put it into a mine site and leave it for 20 to 30 years without a lot of action is doing a better job at the installation, the quality control. Again, focusing on iron. I've done this myself. This is actually one of my pictures from a barrier we did with a continuous trencher in Scarborough, maybe 10 years ago. You're using a magnet to try to pull the iron out of the mixture, and then you weigh the iron and you hope that you're kind of guesstimating how much iron is in the mixture. Takes forever, extremely low accuracy, very subject to human error. This is a magnetic susceptibility meter. So what we're doing is it's a simple contact measurement. Once you have it calibrated, look at the response curve here. You get wonderful calibration curves on most simple iron mixtures. And then this is Mel. She's actually very senior, the lead tech here. Her measurements are taking less than a minute to assure you that you've got exactly the amount of iron in the ground that you have, and you're doing multiple samples, so you know that the distribution is also meeting your requirements. Literally, the detection is down to 0.1% by weight, so you become comfortable with putting in 1%, 2%, 3% iron, if that'll work. You have that type of control, and you verify what you've done. And I have some hidden slides. I'm not going to bring them out in the interest of time, but there are similar field testing methods for some of the sorbents. We have a field testing method for one of the PFAS sorbents. So again, why are you building a barrier if you don't know what you put all this design effort in? You can verify what's in the ground. You can make sure that it's evenly distributed and you're getting the minimum dose. Huge for performance. Field performance monitoring, we haven't had the same types of quantum leaps in new methods. I will say that it's a lot easier nowadays with data logging and with telemetry to monitor simple control parameters like pH and ORP. So we can say that the barrier is in the zone in which we want it to be. It is performing as expected. That's easy to monitor with relatively low effort over long periods of time. I will say that what that doesn't show you is that the contaminants are actually destroyed. You still have to go back out there and validate that when the barrier is in the control limits, it's still doing what it needs to do. So you will still be going out there to do the analytical chemistry. But when you're not there doing the analytical chemistry, you can check these other indicator parameters and see that you're still in that zone. So that would let me, if we have time, and I think we do, let me do a quick case study because everybody loves case studies. And we picked one that actually tries to blend some of these advances all in one wonderful case study. And it is probably the only case study you'll ever see of somebody doing, it sounds like belt and suspenders, but there's a rationale. I'll explain why. It's both injected and trenched PRB, same site. It is a former lead smelter. We did this in collaboration with Milestone Contracting. So VEI did a lot of the testing. VEI did the testing. VEI did the design. VEI did the injection. Working with Milestone, who's a very, very highly qualified contractor with the yellow iron, the operators, and so on. Huge impacts here, right next to a river. And so you've got very highly impacted, metals impacted groundwater daylighting into the shoreline. Specifically, when I talk about high levels of impact, the arsenic levels in soil were so high that the soil is actually has waste. It's like leachate toxic. So you've got 200,000 part per billion arsenic in the source area, and it's all wanting to go down towards the river. So this client actually went to market looking to do pump and treat, potentially forever and ever and ever. Like that's and pumping, and it's fun to do pumping system. I don't know if you've ever done a pumping system next to a river, but it's really a lot of fun to try to design a pumping system that will not end up pumping and treating the river itself. A lot of issues around that type of intervention. And so the two firms working together came up with an alternate proposal, which is, look, let's use this semi-passive intervention. Let's intercept it. Now, you got a problem here, of course, which is that you can't do this trenched barrier literally in the water, and you have a whole bunch of highly impacted material that's still there. So I don't know. This is actually, there may be a couple others out there, but as far as I know, this is the only specific case study I'm aware of where somebody has a really good design rationale to do injection, down gradient to the barrier alignment, and then a full-on funnel and gate barrier. So these wing walls are a low permeability bentonite mixture, and it's funneling all the groundwater through a single controlled reactive zone. We can argue the merits of continuous barriers and funnels and gates in a different webinar. But here, the first step was to inject a slew of iron. Again, if you're from the mining background, hey, wait, those look like chemgrouts. Those are just basically slurry mixtures that are then feeding a direct probe injection, a direct push injection unit. And you're overlapping, or we're overlapping a lot of these to get material into the ground. It's a microscale ZVI. We actually have the capacity, we're not super special. The industry, any of us have the ability to we can get sulfidated ZVI, we can get microscale ZVI, we can get macroscale ZVI, we can get ZVI in a gel, you can get ZVI. There's lots of things we can do with the chemistry. It is a highly mature technology. And then the trench, right? You can see on the left-hand side where the bentonite barrier is directing groundwater through the trench. That's the trench that was backfilled with a simple iron sand mixture. You can sort of start to see some of the markers in the background of where previous injections were. That'll become important when I show you the data, because obviously your question is, how does it work? So let's review the configuration here. Okay, so up gradient, we have this MW3. It looks like an 8. It's actually a 3. The line's poorly placed. Note that well. We have one well. It's actually in the gate. So what is happening chemically in the gate? And then we have one well, MW9, down gradient to the gate, immediately down gradient to the gate. So, okay, in section, source area, MW3. It's going through this 40% ZVI mixture. You know it's a smoking hot site when we put 40% iron in. And then it's on the down gradient side, close to it, we actually have the monitoring well. And what happens? Well, up gradient, here's your blue line. That's the up gradient arsenic concentration. So obviously the construction activities, you have a lot of hydraulic perturbation. You have a little bit of anarchy around the injection and trenching point. But then after that, the source area resumes being the source area, very high concentrations. Down gradient to the barrier, immediately a significant reduction. And then it kind of plateaus. So you're seeing a huge reduction, but it's not going to zero. So this actually, believe it or not, vindicates the design, right? Because in the barrier, we can measure what's happened to the arsenic. And in the barrier well, right, the arsenic's all dropped out. What is happening down gradient of the barrier? That was all the material that was residual in the soil from the years and years and years of this ongoing source to the river. And so fortunately for this owner and for the river, that whole field is a reactive zone. We've got injection points going almost up to the riprap, and that entire zone is clearing the arsenic with the same chemistry that's active in the gate. So overall results, this is half the price of pump and treat, right? Over the span of the analysis. The 2 stages, although it seems excessive, had a careful design rationale, and we backed out of it after about 7 years of monitoring, and at 7 years of monitoring, it was performing as expected, right? So that secondary treatment through the injection in this specific case was actually fairly clever. And within the PRB, 99.98% reduction in dissolved arsenic sustained. Closing thoughts on PRBs and their application to metal leaching, given the advances that have been made in PRBs for many different applications. So clearly, PRBs have been in one form or another on mine sites forever. As far as we know, so PRBs are now so mainstream that no one keeps a register of how many PRBs are installed. So I'm old enough to remember the 2010s, maybe up to about 2012, 2015, people attempted to keep a list of all the PRBs because this great innovative technology. And since then we stopped. So when we stopped counting, there were somewhere around 250 to 300 PRBs that had been installed and documented in the literature. Now it's many hundreds. Of those, about 30% were going in for inorganic constituents. Variety of many dissolved metals, some radionuclides. There are a couple of different formulas. Only about 10% of those PRBs were going into mine sites. Now, part of that is that many mine sites have been allowed to kind of run on a monitoring basis for a while. But we probably should be looking at PRBs for more mine sites. They fit exactly. They have a great track record there, and we've now learned more to make them effective, more cost effective, and more reliable. So when you put in a system, you can be comfortable that you're effectively going to walk away for 20 to 30 years. It's suitable for the exact heavy metals that we see on mine sites. We have bench testing protocols to verify that it'll work with the mine-specific chemistry. The application methods allow us to accommodate a wide range of ground conditions, access constraints, grade changes. There are application methods that can be used to, if not build a traditional barrier, then an in situ reactive zone. And so what you're looking at is an extremely effective long-term risk control measure. Another advantage to this is that you have far fewer constraints on surface usage at the site. You may need to come back on the barrier alignment, but especially if it's an injected barrier, it's not tremendously disruptive. And it'll last. It'll last 20, 25, 30 years at least. If you wanted to, one could actually build thicker sections and different initial loading rates to go to, well, long enough that we could expect some other fabulous technology in the future. And from that perspective, especially when you look at the O&M costs on these things, it's actually really, really inexpensive. And I haven't even touched on looking at the overall carbon balance, looking at the overall environmental sustainability of putting something in the ground, walking away and being able to rely on it as opposed to fly in and out crews all the time to try to maintain an active pumping system in a remote site where you've pulled out all the rest of the mine infrastructure. So, and why are we particularly keen on it in 2025? Well, we've learned enough in the hundreds of barriers that have gone in to have comprehensive, reliable conceptual site models. Those with the desktop modeling give us a reasonable understanding of performance, and we also can identify where the uncertainties and sensitivities are. We have site characterization technologies that quickly fill critical data gaps without wasting your money. And then with that data in hand, have a wide range of available reaction chemistries that we can benchtop and column test using thoroughly well understood, reliable protocols with site water to make sure there are no unanticipated problems with reaction chemistry. That allows you to do a design that has targeted safety factors, so enough to be safe, but not so much that it's excessive and dumbly expensive. And then, in installing it again, we have a lot of control now over assuring you that the dose was put where it was supposed to be put and it is distributed across the transect. So that leads to long-lasting, sustainable, reliable PRBs that are tailored to site conditions. It's sort of a cool presentation about innovation, but in a way, actually, if you think about this fits what we do with all our other remediation programs. It's having the three pieces that for successful remediation or risk control on any site. Do you know enough about your remediation design approach that you have enough in site characterization data? Do you have a conceptual site model that is truly sufficient for the remediation mechanism that you're going to bring to the site, right? Second piece, when you design that intervention, do you have enough design information that the design is then truly accounting for the conceptual site model? And then, honestly, if you have those two things, all we need to do is make sure that when you're in the field, it is implemented the way it was designed. And again, with PRBs and with oxides, with many of the other technologies, you need all three pillars. And at this point, those three pillars are quite mature for the PRBs, which have a lot of applications. You may think of PRBs for chlorinated solvents, maybe for hydrocarbons. You need to think about PRBs for dissolved metals. And you need to think about PRBs for dissolved metals in challenging places, including acidic flows, including mine sites with metal leaching or acid rock drainage. So Kevin, I ripped this off of Kevin. Kevin and a lot of the people I work with, for some reason, love Star Wars or Star Trek or whatever the heck that is. So, back in the 90s,
Ouch.
maybe at the ape stage, the old school methods that we've talked about, the rules of thumb, the not fully understanding what had to be in the conceptual site model, times have changed. I'm not going to say that we're at the AI R2D2 USS Enterprise, whatever level that is. But we're definitely we're past the ape stage. We're kind of probably towards a competent workman, I think, a reliable, competent work person. That's it. That's the presentation.
All right, thank you, Pete. Apart from the, you know, science fiction genre mix up there, we'll let that one go. Um, anyway, let's go back to our attendees and see if there's any questions. Please, like I said, put them in the chat or put them in the Q&A, and I can field them to Pete. While we're waiting on that, I do have a couple for you, Pete, and I didn't tell you these ahead of time, so I'm going to put you on the spot. But when you go back to your when you have highly acidic groundwater flow with elevated, sulfate formed heavy metals, and you're going to do one of those buffered PRBs, right? Would you recommend doing sequential PRBs of like buffering agent and then zero valent dye, or would you mix it all together? And
So
why?
most of the designs that I'm familiar with. Okay, so we have a couple of different things that are going to influence that choice. It's a great question, and a couple of things are going to influence that choice. One is what does Bruce tell you have to do? No, from an engineering perspective, one is how are we going to place the barrier? Because although we can in place a lot of materials through injection, limestone pebbles are very hard to in place through injection. So assuming that we're doing a more traditional type of barrier, it is very, very common, and there's no reason not to, for simple pH and chemistry problems to actually mix the limestone with the ZVI. I think the PEC barrier, I think I mentioned it in the presentation. So actually, even that, well, the Falcon Ridge barrier didn't actually have iron in it, but they're ratios of like, I'm going to use so much mulch, I'm going to use so much limestone, I'm going to use so much gravel simply for perm and for bulk, and then I'm going to use so much iron. And that's mixed together, sampled, put in the ground. Um, the reason why I'm hemming and hawing is because there have been a couple of places, not so much with pH, but I'm aware of one case, and it was an Australian barrier where it was actually high nitrate was impinging on the potential iron wall. And so one of the things that can happen with high nitrate is passivation of the reactive surface of the iron. And so in that case, because you needed to clear the nitrate entirely, or not entirely, you need to clear the nitrate enough before it hit the iron. It was actually two sequential barriers. In that case, it was a sawdust barrier, up gradient of a more conventional trench type barrier. We could obviously, as you know, we can obviously inject a lot of carbon sources other than sawdust in a reactive zone up gradient to manipulate the redox conditions and eliminate the nitrate before it hit the iron. So I find mixing in the limestone, make sure it's good limestone, test its buffering capacity, consider the particle size. Most cases, you can mix it directly. In some cases, and maybe not pH, but for example, with the nitrate, you may need to actually work up gradient because of the sequence of the chemistry.
Mhm. Yeah. Yeah. The other consideration too, one I worked on a little while ago was that the calculated lifespans were different of the media. So the buffering agent was going to only last like 5 years, whereas the ZVI was going to last 20 years. So it was done as a separate trench, and that's relatively less expensive media. So you could easily dig it out and replace it once it lost its effectiveness. Okay, so we have a couple questions here. The first one, I'm not sure exactly. I'll pose it to you, but we may need to ask the person answering it to or asking it to clarify. But it says, can PRBs be adjusted after new municipal wells are built in the area? So I'm not sure exactly what that means, unless you do, Pete.
Well, if you want, Lily, if you want to ask more detail, we can handle it. Just off the what I would suggest itself is to say that if you start any type of sudden change in hydraulic conditions, that all of a sudden you fire up a new municipal well that starts changing groundwater flow paths, um, can you adjust your PRB? Um, Well, it's much easier with an injected a reactive zone than with a trench. Obviously, with a trench, then you're going out there and you're now building additional wing walls or attempting to build additional wing walls. With reactive zones, you're just going in there and building because there's additional like injection field areas. I would probably municipal wells don't typically spring out of nowhere, so that would be something that you would want to look at very carefully before designing the initial barrier. Um, that you've allowed for the possibility that somebody is going to suddenly change all the flow paths and the entire potentiometric surface in that area because that's changing the velocity through the barrier. It's changing the changing seasonal fluctuations. It's actually changing flow paths. So it's complicated. You might end up in a situation where you're effectively building several subsequent barriers, but there's no hypothetical reason under most scenarios that you couldn't do it. It would be way, way better if you saw that thing coming before you actually tried to put the first barrier in the ground.
Hmm. Hmm. Okay. Thanks. Next question is, can you explain a bit more about the injection points, grout curtains that are reducing bypassing of the PRB?
So I was comparing. Hopefully, I didn't get too confusing. I was because in mining, and I've done enough work with guys, especially on dams and dam toe reinforcements, that it's very common to inject low perm materials to do a seepage cutoff. So I was just trying to make the comparison to traditional grouting techniques because mining people would be comfortable with that. It's a good conceptual framework. We typically have not used injections to build the low perm wall sections. Generally, with the injection type barriers, they tend to be continuous reactive zones, and you're not necessarily attempting to funnel flow through a specific gate with a high concentration. You could, it just hasn't been commonly done. What is commonly done for hydraulic for bypassing control in a traditional barrier construction is you would do long, low permeability walls, wing walls that are typically bentonite or a bentonite derivative, cement soil bentonite, so a mixture that will have low permeability once it's put in place. And that wall is then shepherding all the water through a specific reactive gate. Um, there, we were, I was involved in a project, very interesting project. We didn't even talk about it, but in the 80s in Europe with Soltanche and a couple of others, there was a lot of interest in building underground passive treatment systems. And so you would basically build underground drain systems or diversion systems or even simple siphon systems. And what you were doing is you were putting your reactive material in an engineered cell or in a container and having passive gravity flow through replaceable material in a cell. Um, you can imagine that you don't need to pump if you actually, for example, if you took something off a hill, you could direct it down through a contactor and then out again, right? You don't have to actively pump. So there was recently a job, Canadian Forces Base in Canada for PFAS, not for metals, where they built the wing walls. The wing walls were supposed to be built actually out of Waterloo barrier. That ultimately turns out that there are cheaper, faster, better ways to build load perm wing walls and guiding through a reactive gate. So you could do sheet piles into a reactive gate. That was a very interesting reactive gate because that designer was actually divided it into cells so they could evaluate different materials in different cells and if necessary replace them. Um, yeah, so there's a question about sulfate concentrations in the PRB. Iron will drop sulfate by itself. And if you put a whole bunch of organics in place, what you will do is drive typically, not always. So under normal conditions, if we put a whole bunch of organics into a high sulfate dissolved stream, you get into basically sulfate reducing conditions. And so natural biological activity is going to eat organics using sulfate and produce sulfide. And so you get hydrogen sulfide or you get metal sulfide through biological action, but the sulfate levels have dropped. Yeah, this is a good question. Finding good limestone, it can be a real challenge. Um, could ZVI be prohibitive for ARD or ML result associated with large tailing storage facilities? Any examples of PRBs at large mining sites? Is this marginal for mining applications? I think it's specific to groundwater problems. There is actually so so just I'm not you're not wrong. You're absolutely not wrong. But remember, if you go like to the guard guidance, if you go back to actual acid rock surface water quality management, recommendations, a lot of those systems also require a buffering rock material. Like you're not building an anoxic limestone drain without limestone. So we all kind of so it may be that the PRB is not wickedly cheap, but it's probably not at a cost disadvantage compared to other systems that would also need that buffering capacity. It would be interesting to look at the specific water chemistry and do the column tests because how important is the pH control in that application? If the dissolved metals are managed, do you need to get the pH to neutral or not? This would be a very interesting question. I think so. Kevin, you can jump in, but I think it's a really, really good point that high quality buffering material is not often available at every site. But I still think that there are tools to look at whether there's a viable design without it.
Yeah.
Like super fair point in the sense that if you had a whole bunch of good buffering material, you probably wouldn't have an acid bind problem. You probably have neutral, metal enriched neutral drainage, but you probably wouldn't have an acidity problem if there's a ton of good limestone around. But anyhow,
Yeah, it's a really good question, there's a lot of variables there. So, zero valent iron itself will bump the pH up a little bit. And you're right. It's what is the performance metric? Is it the pH or is it the metals that are dissolved? And if it's the metals, then maybe it's just a function of increasing the contact time. So maybe your ZVI design is maybe more heavily loaded, or it's a wider trench that it's passing through. But it also depends on the drivers because, one extreme case that I know of, they actually shipped a very specific dolostone from Ontario to BC to put in a mine, PRB, because the discharge standards were so critical and so sensitive. That was the only buffering media that would work. So, it depends on the drivers and then what the regulatory pressures and things like that are. But you're right. You're right, Pete. Um, all right, there's another one. Okay. One of them just say they're happy they joined because it's a good presentation. So thank you very much for that.